We're going to talk about hyperbolic functions, and they're sometimes called hyperbolic trig functions. First of all, because you see trig functions in their name, but also because they have many of the same properties as their analogous trig functions. Well, certain combinations of e to the x and e to the negative x show up frequently in engineering and physics applications. As you go to solve something, you get this combination. And so we have defined these, and when we have an e to the x minus e to the negative x over 2, and it could also be expressed with that factored out in front, we are going to define that to be the hyperbolic sine of x. So it's written like this with a sign but then an h after it, and it's actually pronounced cinch. Don't ask me where the ch comes from, but this is pronounced cinch. Okay, well, what would this graph look like? Well, we're adding these e to the x and e to the negative x, but we're actually subtracting those, and then we're going to divide them by 2. So if x was large, this is going to dominate, and this is going to go to 0. But if x was negative, this exponent will be positive, and this one will be negative, and x gets large negatively, this one is going to dominate, and this one's going to go to 0, but this one would have a negative sign on it. So it's no surprise when we kind of look at the graph, as we go to infinity, we would be approaching infinity, and the limit of this hyperbolic sign as we go to negative infinity is negative infinity. Now, another thing that's interesting, if we take the limit as x approaches infinity, this term here is basically going to go to 0, and so we would have 1/2 e to the x. And that in fact is what the graph approaches. This red is the graph of 1/2 e to the x, and you can see as we get larger with x that we do approach this graph. Now the hyperbolic cosine, and that's pronounced cosh, and that's what it looks like, is the same thing except it has a plus sign between the two exponential functions. So it could be expressed like this as well. Now if we thought about what this graph would look like, we are actually adding these two together, and so we see that if e was becoming larger and larger positively, this would dominate and this would go to 0, and we would approach 1/2 e to the x. We could see if we were looking and becoming larger and larger in the negative direction, this would become basically an e to the x, and this would go to 0, and it would also approach a 1/2 e to the x, but as we're over for negative values. So this is what the graph looks like, and it's interesting. You can see that we would always get a positive number here, and you can see here then, because we couldn't ever have these being, opposite signs or anything, you see we always get these positive values. And if we took the limit as x approached infinity of this last term would go to 0, and we would be approaching 1/2 e to the x again, which you can see if we put that on the graph. Now, something interesting here is if you evaluate these at 0, cinch of 0, if we had put them in here, we would have e to the 0 minus e to the 0, so 1 minus 1 is 0, so the value of this would be 0. If we put it in the cosh, we would have e to the 0 is 1 plus e to the 0 is another 1, so we'd have 2 over 2, which is 1. And the sine of 0 is also 0, and the cosine of 0 is also 1. So they follow with their trig functions for that property. If we evaluate them at 0, they have the same value as the trig functions that are in their name. Now the hyperbolic tangent then is formed by simply taking the hyperbolic sine over the hyperbolic cosine, just like tangent was sine over cosine, so that's an analogous thing as well. So the way we get at it is we basically take those definitions, and then we can see that the 1/2s would cancel, and we would have this, and here is what the graph of this would look like, because you can see the limit as x approaches infinity, these last terms would go to 0, and we'd have e to the x over e to the x, so it's going to approach 1. If we looked at negative infinity, then here we'd have e to the negative x, so that would go to 0. This one would become positive, but it has a negative sign on it. This one would go to 0, and this one would be an e to the positive number by the time we put in that negative, and so we would have -1. And so you can see the limit as we approach negative infinity is -1. So anytime we need to utilize these, if you want to, you can write them out in terms of their definition. Now, sometimes it's useful to go the other direction. We essentially get something that looks like this, and we could write it out in terms of a hyperbolic sine. Or if it looked like this, we could write it in terms of a hyperbolic cosine, and then we could use their properties, and it just makes them a little easier, a little less messy to work with. So the name hyperbolic, where did they come up with that? It comes from the fact that if you took x and let it equal cosh t and y and let it equal sinh t, these would be parametric equations for the right-hand branch of a hyperbola that equaled 1. And so that's why we call these the hyperbolic sine and cosine. So x is cosh, y is sinh. So if we plotted these, so as we let t increase and we plotted the xy values, you can see what happens here is we end up tracing out this right-hand branch of the hyperbola. Now what about the derivatives of the hyperbolic functions? Well, if we need to find the derivatives, essentially what we're going to do is we're going to put them in terms of the definition, the exponential functions, and we know how to take derivatives of exponential functions. So let's do that. We're going to start with hyperbolic sine, and if we want to find the derivative of this, I'll just use prime notation, then we could take the derivative of this. So that's going to be 1/2 derivative of e to the x is e to the x, and then minus the derivative of e to the negative x is e to the negative x, but then the chain rule applies, multiplied by the derivative of negative x, so that will make that a plus. Oh, well, that's the definition for the hyperbolic cosine. So the derivative of sinh is cosh, analogous to the derivative of sine is cosine. So there's an analogy there as well. And then of course if it wasn't x, if it was some stuff, something else, a u, then the chain rule would apply. The derivative of hyperbolic sine u is hyperbolic cosine u times the derivative of u. Now you would probably be tempted to say, okay, the derivative of cosh is negative sinh then, but it's not. It's actually just the sinh. Okay, so the derivative of hyperbolic cosine is hyperbolic sine, no negative. So there are some differences in these. They don't follow exactly. And we could find that out if we wrote out the definition and said, okay, I'm going to take the derivative. So this would be 1/2, the derivative of e to the x is e to the x, and then the derivative of e to the negative x is e to the negative x times the negative, and you can see that that gives us the hyperbolic sine, no negative on it. Now we could similarly do this for other functions. There's other things we can do. We can say we'll do the Pythagorean identities hold, do the double angles identities hold and things. There's actually a lot of trig things that do hold. Sometimes they have opposite signs on them, like we just saw here on the derivative of cosh, the derivative of hyperbolic cosine. So we have to be a little careful. Here is a table, and notice some analogous Pythagorean identities, and let's have a look at those and kind of compare. Here is the fundamental identity, but in terms of hyperbolic cosine and sine, and it's different. We know that cosine squared x plus sine squared x equals 1. With hyperbolic functions, it's a negative sign right there. But these identities can be useful to you. Here's the other two analogous Pythagorean identities, and you can see that they either match or they match except for some negatives in different spots. And also here is like the double angle identity analogy and half angle identity analogies. And then here is our list of our different derivatives. And then here is some integrals. Bottom line, when you're working with these, if you say, I'm not quite sure what it is, you can write it out by the definition, 1/2 parenthesis e to the x plus e to the negative x, or e to the x minus e to the negative x, depending on which you had. And then you could go from there. Now this useful hyperbolic function properties table is also going to be posted following this video.